But my mom enjoyed my pain. She sat there and relished in my pain.
She was like, yes, science experiment.
Science experiment.
Feel the pain.
She was like, it's only at power level 1. Come.
She was pro-hand.
Okay, that should be enough time for our camera to warm up. Lights are off. Good morning, everyone.
Good morning.
Welcome back to Physical Geology 1403. Today is our last lecture
Oh.
ever,
Oh.
unless you take 1404.
Yeah.
It would be really cool to see y'all in 1404. I haven't actually looked to see who is in 1404. I'll probably look later today. You are?
Yes.
Nice. You are? Yeah. Anyone over here?
Historical geology,
1404?
Yeah.
Anyone in 1404? You're gonna sign up today? I love it. I love it. Okay. Well, taking 1403 is a prerequisite to 1404. So I always know the people I have in 1404. We've already got history. You're already familiar with the way that I teach. There's very little learning curve. And I'm often told that 1404 is way easier than 1403 simply because you're already used to the ways that I teach, the ways that labs go forward and all of that. So you're already there. It's kind of just continuing that high. All right. Let's see. What's new? What's going on? Any questions? Anything we want to talk about?
I'm still trying to remember my weekend over here. Don't mind.
Anthony is still trying to figure out if he's a robot. He cannot remember his weekend, so someone must have wiped his memory.
Yeah, I can check my Google Maps. It should say where I
Check
am.
your Google Maps.
Yeah,
He
Google
was
Maps
in
has-
Cambodia and he does not remember. Yes.
I hated your live exam. Those videos were so glitchy.
The videos were glitchy?
Yes, did you look through them? They were so glitchy.
They're the same videos I've used for about 3 years now.
You need to update those, because those are
Hmm.
I could hardly see it all.
Like they would stop and
Yes.
keep going. That's probably an internet thing.
I tried to download it. I have very good internet.
Mine was
Okay.
It's literally
Yeah, they were just fuzzy. The videos just looked fuzzy.
Were they stopping and starting for you?
No, it was just fuzzy looking, like the quality was bad.
it wasn't clear. You couldn't
Yeah.
see it very well. It was just kind of glitchy.
And then the camera would focus up like a little bit and then just
You could see.
You had to wait 10 minutes for them to load. That sounds like an internet thing. Okay. All right. I will revisit remaking those. I haven't really had a whole lot of people complain about the quality of the videos before, but Blackboard is always changing their optimizations. So what may have been a good video before, in light of the most recent updates to Blackboard this year, may no longer be sufficient. So I will take a look at those. Where are my
I
post-it
remember
notes?
what I did now. I remember what I did.
You remember what you did this weekend?
I got my memory back. I stayed at home all day.
You stayed at home all day.
Yeah, I got my hair done. My
It-
mom did my hair.
It
I
took you
watched-
10 minutes to remember that you stayed home all day?
Well, yeah, but I did stuff while I was home. Like I got my hair done. I watched Sonic 3. It was on Paramount Plus.
How was it?
Sonic 3. I watched it in movies too, but
Oh, it's on Paramount Plus?
Yeah, it's on
I'll
Paramount
have to
Plus.
watch that with my son tonight. He loves Sonic.
Yeah, it's a really good movie. 10 out
Look
of 10.
at lab
Did you used to
exam.
play like the old Sonic games, like Sonic Adventure?
No. The first video game I ever played in my life, I was 15 years old. It was Halo 1 on the original Xbox. I never played any Nintendo. I never played any old games of any kind. Halo is the oldest game that I've ever played.
The first game I ever played
Huh?
was Halo
That's
3.
crazy because my first games I played were like on the old Nintendo.
Yeah.
Nintendo I have is like the first Nintendo ever made.
Those are still pretty popular. But yeah, that was never a part of my childhood. My parents were never into video games. Matter of fact, bless you, that first time that I did play Halo, they were rather upset that it had occurred. So that was the first time I played a video game. The first video game console I ever owned, I was 17 when I got that, and that was an Xbox 360. Yes, those have been around that long. All right. Okay, I will look into that for sure. I will try and sort that out. I apologize for the quality. Although I will remind you, actually taking it with an actual in-person set was an option. I'm just going to put that out there. It was always an option. Some of you, I think 2 of you actually did that. The rest of you opted to watch the online stuff. So Yeah, you have a question. Oh, okay. Okay, any other comments? I won't discuss any topics from the exams specifically because I am still waiting on a few of them. Dun, dun, dun. If you have not taken exam 1 or exam 2, excuse me, exam 2 or the lab exam, do it ASAP because your final does open today and you do not want all of that piled up on you. What else? Interesting stories, news?
A couple of things that happened at my
Ruffles and feathers? Nothing ever happens in America that would ruffle feathers.
There's was it a conference with the Ukrainian president?
Right. The press conference with the Ukrainian president. That was delightful. Yeah.
The last day of grading will be on the 6th, right?
Wednesday, Thursday. I will be submitting final grades on Friday, but I will be closing the class on Thursday at midnight. Make sure everything is turned in by Thursday at midnight, or else you may, if you put off taking the final until Thursday at 11, midnight will roll around, then all of a sudden it will say you have been locked out of the course. Don't do that. Okay? Good questions. Do y'all know that English is now the official language of the United States?
What a shocker.
I know. I spent my entire life wondering what the official language of the United States is. I couldn't possibly have gone on Wikipedia and figured out what the most spoken language in the United States is. That wouldn't have been possible. But now that it's official, I know my soul is at rest. Okay.
Protective president.
Oh, yes.
I also like how none of these are bills passed. They're just all.
No, they're all executive orders. He doesn't have time to send things through Congress.
Because changing the official language to the language you already use
Right.
everywhere is
Right.
that's
I don't
needs to
want
be done.
I don't want to imply that I lean one political direction or another, but I will say one more comment before we move on. He said, I'll be dictator for the first day. And here we are still making executive orders. And that's all I'm going to say on the subject. All right. Anything geological, anything interesting, scientific we want to discuss before we move into the new stuff?
I don't think nothing geological has happened over the weekend.
Nothing geological has happened? Oh my goodness, the Earth has stopped working.
Yeah, pretty much. We've been still.
Earth is no longer dynamic. That's good. Right, Earth is not earthing right now.
Earth is not earthing.
Okay. Well, if there's nothing you have questions about, then let's learn about some new stuff, right? The last new stuff you're going to get, and hopefully some questions come from there. Before I go to the next slide, let me just ask this. What are mountains?
Results of sorry.
It's all right.
The results of convergent boundaries?
The result of convergent boundaries. Okay, so this is utilizing some language, some processes that we've already learned about. You're absolutely right. Mountains do occur at convergent boundaries. Not exclusively there, but very commonly there. Why at convergent boundaries? Who's got squeaky shoes?
It's not shoes.
Oh, it's your laptop. Okay, okay. All right. Why do we get mountains at these convergent boundaries?
Because the Earth.
Someone not Anthony, because you brought us the first half of that answer.
Fair enough.
Because the crust is moving into itself and it has to go somewhere.
The crust is moving into itself and it has to go somewhere. All right, sure. I like, in particular, that second part. It's got to go somewhere. So where does it go? Up and also down, by the way, right? The roots of mountains go down very far, usually further than they go up. Okay? So, mountains are sections of Earth's crust that have been pushed up, or uplifted is that term, due to some tectonic force. There are a couple of different forces that can make this happen. It all comes down to the interaction between the materials and the force applied. different materials will respond in different ways to different types of forces. Okay, so everything from the breaking point to the melting point, the metamorphism point, all of these things that you've already learned about, which the characteristics of a rock come from the characteristics of the minerals that make that rock, right? These are all things that you've learned over the course of the last 7 weeks. All of these properties add up, one variable at a time, to the conditions that would allow for mountains of one kind or another to form under the right conditions. So we've got several different types of stress. Compressional stress, which you would find in Anthony's example of a convergent plate boundary, right? Where you got forces pushing towards each other, making these, what term did we use for these when we learned about metamorphic rocks? Not foliations. Very similar. Bless you.
Thank you.
Huh?
Differential stress.
I mean, differential stress is making this happen, but what do we call these changes here? If I were to take a blanket and then bend it over in half, and then bend it in half again, huh? Folding, thank you, yes. The rocks are being folded by these forces, these compressional forces. Then we have tensional force, where you've got a pulling and stretching. What kind of plate boundary would that potentially occur near? Divergent, yeah, where the plates are pulling away from each other. Yes, that's called tensional stress. This causes a thinning of the crust here, but what that means is you actually get a thickening of the crust on either side of that thinning area, okay, by contrast. And then you get shear stress. Shear stress is kind of like this compressional stress, except you've got different depths involved here, okay? So instead of two forces directly pushing into each other, maybe you have a force that's pushing this way and a force that's pushing this way. They don't directly push into each other, but they are causing the material between them to kind of get warped into this diagonal sort of stretched sideways pattern, okay? Shear stress. The 3 kinds of stress. It is shear stress that builds up along fault zones, okay? Now, our materials can react in a couple of different ways. The ways that a material changes in response to stress is called deformation. You've got elastic deformation. Again, I'll use the example of our friend the rubber band, like when I talked about last week during earthquakes. You pull and you pull and you pull, and you're adding elastic stress, that elastic energy, until finally the energy of that material overcomes whatever material is pulling on it or pushing on it, okay, in the situation, and the stress is released, okay? That's the elastic limit. At the elastic limit, material will either break, that rubber band could have broken, right? Or flow will occur. In the case of this example, the material slipped out of the guy's finger. Why? Because the stress built up inside the material overcame the friction of the fingers holding it in place. Okay? One of those things will happen. That's elastic deformation. Then you've got brittle deformation. With brittle deformation, something does not bend. It does not reshape itself very easily. And so instead of staying in its nice uniform shape and simply bending or changing, it breaks into smaller pieces. It shatters, okay? We've all had days like this. This poor guy's window did what? It didn't bend, it didn't. Yeah, it shattered. That glass shattered. That is brittle deformation. If I were to take a chunk of granite right here and a giant sledgehammer and just wail on it, it would shatter, right? What would happen if I put a ball of Play-Doh here and I wailed on it with a sledgehammer? Would it shatter?
No.
Yeah, it would flatten. That is called ductile deformation. Ductile deformation is when you can take a material and apply forces to it, and it will simply maintain the same shape caused by the forces that you applied to it. Do you remember a material that we got a lecture on not long ago where we discussed this kind of deformation. A material that will deform itself under the right stresses, that will perhaps flow ductily.
Water?
Not water. It's got to be a solid in this context. No. Water was kind of on the right track.
Iron?
Not iron. Iron is to an extent, but it takes more effort. Huh? Not magma. Ice. You remember how we talked about ice flowing? Right? That ice flowing is under the influence of stress. It's reshaping itself ductily, just like this Play-Doh does. Okay, so what are the things that control what sort of deformation happens and how that deformation progresses? Temperature is a big one. I've given you this example before, but what's the biggest difference in your mind between a frozen Hershey's chocolate bar and a warm Hershey's chocolate bar? I'm not talking about a room temperature Hershey's chocolate bar. I'm talking about a warm Hershey's chocolate bar, one that maybe you left on the dash for a minute too long, right? What happens if you try to bend the frozen one?
It's going to be harder.
It's going to snap. It's going to break brittly. What happens if you try and bend the warm one? It's a little squishy, and so it'll bend over, right, without actually breaking. So here we have the same material. And I'm sorry I'm talking about chocolate right now. Everyone's probably hungry. But for some reason, cookies and chocolate, it comes to my mind whenever I'm teaching these classes. It's just an easy example for people to get, you know? So the same material deforming in two different ways based upon what? The temperature. Rocks are the same. So I can have a warm rock that is more likely to deform than a cold rock. Can you think of an example where this happens? Deforming warm rocks. Metamorphic processes, yes. Sure. Can you think of something we've talked about over and over and over, a layer of the earth where this is constantly happening?
The upper mantle.
The mantle. The mantle is constantly deforming ductily. It is solid. It is really hot, though. So it can ductily flow under forces that are causing it to. And that is called convection. Remember that? So here on the Earth's surface, how cold is it up here? How warm? Is it pretty cold compared to the mantle?
Yes.
Are our rocks up here more or less likely to flow ductily or brittly? Brittly, yes. Do you remember the last time we met? We talked about earthquakes and faults, and I mentioned that most faults occur in the shallower crust, the top 15 kilometers or so of the Earth's crust. Why?
It's closer to the core.
The crust is closer to the core?
No, sorry.
Rock is more brittle up here. Why is rock more brittle up here?
It's not its
And lower temps.
Temperature is what I'm looking for here, right?
It's not the conditions it's used to.
Okay, so that's stability. That's stability. That's not so much at play in this example. It's always a factor everywhere, but not what I'm looking for here, okay? It has to do with the temperature. The rocks up nearer the surface are colder than the rocks that get down further below. So the rocks up here will deform brittly, aka crack, and make faults, and the ones that you get lower, further down underground are warmer and therefore are more likely to deform ductily. And is it really possible to make a crack in Play-Doh? Like fresh, nice Play-Doh. I'm not talking about old Play-Doh you left out overnight, right? Not really. You try and pull your Play-Doh in 2 different directions, and it'll just deform ductily. Whereas if I froze that Play-Doh and then I tried exerting that force on it, it would crack, right? Temperature affecting the same materials differently. And that is why most earthquakes occur in the top 15 kilometers or so of the Earth's crust. And there are much fewer the deeper you go underground, because faults don't generally occur that easily. There are some big faults that go that deep, but most smaller faults remain in the top 15 kilometers. Okay, and then there is pressure. Shear stress is a kind of differential stress, which is responsible for making a lot of those faults. But confining pressure can also play a role in the deformation of certain materials. Have you ever heard of the term salt dome? We live out here in the oil field, right? Salt domes are very important in the oil industry. Some materials are more likely to deform ductily than others. For example, granite, not likely to deform ductily. But limestone, pretty ductile, at least compared to granite. Shale, not usually. That's usually pretty brittle. Sandstones, usually pretty brittle. Salt. Salt is very ductile. Under what conditions would I have a whole layer of salt underground, though? Picture this. The Gulf of Mexico, right now. I cut it off. I stop it from any interaction it has with the ocean. Yes. Gosh darn it. The Gulf of somewhere. The Gulf down south. The Gulf that currently has a lot of salty water in it, right? I cut it off from the rest of the ocean. We talk about how that may have happened in a minute, but let's just say that I do. What eventually happens to all that water? It leaves? It just goes on vacation to Cabo? What are we talking about? It evaporates. Good. That water evaporates, leaving behind salt and everything else that was dissolved in it. Usually a lot of salt and gypsum and a few other residual minerals, but most of it is definitely salt. So at some point, tens of millions of years ago, this is exactly what happened. We think that the ocean levels dropped a bit and some tectonic forces caused some uplift out there in the ocean that cut off what the body of water that currently inhabits the Gulf area would have been at that time. It wasn't the Gulf. It didn't look anything like that, but there was still water there. It cut that area off for a couple million years at least, which meant that all that water eventually evaporated away, leaving behind thick deposits of salt. Okay? Hundreds of feet thick. And then, of course, all that went away and the water came back in and we have our current Gulf of Mexico. But the point is we have very thick layers of salt underground in the southern United States area. In the Gulf area, in Alabama, Louisiana, southeast Texas. Okay, a lot of salt is underneath of that. Now, salt, because it is so ductile and it's under a lot of pressure at those depths that it's at right now, if there is the slightest little crack, the smallest outlet on the layer above it, it's going to push its way up into that. It's going to shove its way up to the crack. And in the same way that water slowly weathers and erodes material as it goes through, the salt does the same thing. It makes the crack wider and wider and wider until you go from having a flat layer of salt to a bunch of it has pushed its way up to lower pressures. It's trying to get up to the surface, right, where the lowest pressure is, just like all fluids and, turns out, some solids under pressure will try to do, right? It's pushed its way up through this shale. It's pushed its way up through this sandstone. It's pushed its way up to this limestone, but it can't get through it. This is a ductile layer. Instead of cracking and breaking and allowing the salt to pass through it, it has ductily deformed above, effectively capping that salt dome. Now, why does this matter to the oil industry? Well, let's say that oil is flowing through this system. It often does. We have some limestone here, some sandstone. Sandstone, great reservoir rock. Has a lot of porosity and permeability typically, which, as you may recall, are great for storing liquids, including oil. So oil is flowing through the system, through the sandstone, but wait, it encounters the salt dome. The salt dome has pushed up on the layer above the sandstone, effectively making a zone in that sandstone that is at a lower pressure because it is at higher elevation. And so the oil will pool around this salt dome in this sort of crown of lower pressure at the top of it. And so, and this is, think of this in 3D. This is a whole, crown that goes around the salt dome, right? And so it is actually very common in the United States South petroleum industry to look for salt domes, specifically so that you can drill around the periphery because there's probably salt, or there's probably oil around that salt dome. We actually have one not far from here. If you're ever on your way down south to Big Bend and you take Farm to Market Road 1053, you're going to get to a point where you're driving around, it goes from the straight road to all of a sudden you have to deviate left and you go in this big wide loop around a pit in the ground. And then you get back on your straight path. Why is that pit there? Well, there's a salt dome. And a long time ago, decades back, I don't remember exactly how many, probably 50 years or so, an oil company was drilling around the edge of that salt dome looking for oil. And they didn't plan their drilling activities very well because they accidentally introduced a water source, an underground aquifer, to the salt dome. And what does water do to salt? Dissolves it. And so they accidentally introduced this water to the salt dome, which meant that they started dissolving their salt dome. So as years go on, the pit in the ground that the salt dome used to occupy gets deeper and deeper and wider because the salt is still dissolving away. They actually have to keep relocating the Farm to Market 1053 further and further to the left, going around the salt dome. So just a few things that can happen there, right? You got to be really careful, especially when these things are underwater. A lot of salt domes that are targeted for oil development are actually out in the Gulf. Okay. If you were to look up a salt dome map of the Gulf, you would see that there's dozens and dozens of them out there. Y'all ever been to Louisiana? Yes? I got my master's degree at the University of Louisiana at Lafayette, which meant that I was only about 30 minutes away from a place called Avery Island. Y'all know what that is? Where that is? How many of you like Tabasco hot sauce? The Tabasco factory is on Avery Island. So I went and I visited probably 5 times while I was there. It's pretty cool. They have a really neat process. Okay, so basically what they do is they grow all of their chili peppers there, and then they grind them up, they mash them up, and they stick them in giant white oak cask barrels with a bunch of vinegar and salt and a few other things, and then they cap those things, and then they store those barrels for 2 years in a dark closet, but they have to pack salt around every inch of these casks to keep water out, okay, to keep any water from getting in there and messing with their sauce. 2 years later, they take them out, they crack those casks open, they sift out all of the mush, and then they sell the Tabasco sauce. That's a result of that. But this whole process takes a lot of salt. You have to put salt in the sauce before it goes in the cask, and then you have to have enough salt that you can pack around each of these barrels, and they are generating hundreds of these barrels all the time. Like every time I would go, I'd watch them do barrel after barrel after barrel. They have vast warehouses on this island where they keep these barrels, okay? It's a fascinating process, but it needs a lot of salt. Avery Island, if you look at it on the map, is this oddly circular looking island just right there on the coast of Louisiana. Like so close to the coast that there's just this tiny little, it's barely even a bridge. It's like a land bridge between the island and the coast, right? But but it's a weirdly circular shape because it is the top of a salt dome. They set up the Tabasco factory on top of this salt dome. The Avery family bought the salt dome so that they could mine their own salt instead of needing to pay for salt to come to them, right? If they hadn't, Tabasco would probably be significantly more expensive to bring that much salt to them. But they have their own salt mines on this island. That's why they chose this place. So you can thank geology for your Tabasco sauce. Yeah.
Why not farm for salt with the seawater?
Well, that requires a process where you have to cut a section off from the ocean and allow it all to evaporate, right? So that's a significantly more, what's the word I'm looking for? Complicated process, especially in Louisiana, where every hurricane that comes through will probably destroy your salt farm production anyway, right? Overwhelm your barriers and everything. Whereas with a salt mine, you just got to make sure you don't get any water in it. So you just cap it, you have a door in there, all of that. There's a couple of meters of rock on top of all the salt, probably more, a couple dozen meters of rock on top of all that salt. If you look at their salt mine, it just looks like a door, like a giant metal door. But, you know, when they're ready, when they need a mine, they open it up and then they send their vehicles in and they're just scraping salt off the side of the walls in the mine, bringing it out. And then they just close the door again and keep it safe from the water. Yeah. Okay. Let's talk a little bit more about folds. When I have a fold that has this sort of convex shape to it, we call that an anticline. When I have a fold that has a concave fold to it, this down fold, it's called a syncline. What is it? Say it louder, Daisy. Anticline. What is it?
Syncline.
Syncline. What is it?
Plunge. Plunge.
Not a plunge.
Sine wave.
It kind of does look like a sine wave. Come on, what's the easy answer?
It's a wave.
What's the easy answer? It's easier than that. Huh?
I'm gonna hate myself after this.
What is it?
It's both.
It's both of them. I told you it was an easy answer. Huh? Yeah, they're all folds. That's too easy, right?
She's right.
We.
Technically.
She's right. She's out of line, but she's right.
Yay.
All right. Now, we often find these together, okay? Because the forces that produce one can produce the other. It's kind of a toss-up which one it'll be unless there is some pre-existing tilt here. Now, what is plunge? Some of you tried to guess that last one was plunge. That's not what plunge is. Plunge is the angle at which my fold is going into the ground. Because everything starts off flat, right? There's this thing called the principle of original horizontality.
Oh, okay.
I know. Such a fancy name. What is horizontality?
Does it have to be horizontal?
Flat, right? Relative to our plane of reference anyway, okay? All layers of sedimentary rock are deposited horizontally. That makes sense, right? It takes the least effort for gravity to deposit things on a flat surface. So if everything just starts off horizontal, but we've got layers of rock that are, right? Nothing can be deposited that way, which means that no rock can form that way. Something must have happened between now and then to tilt it like thus. Now what happens if I do have a tilt and then a fold, right? What happens if I have a tilt and then a fold? Well, the angle at which that fold is diving into the ground is called the plunge. So I can say that this is an anticline with a plunge of about 30 degrees, meaning that relative to my flat landscape, it's got about a 30-degree angle. And I can say it's going in the northeast direction. So I would describe this as a 30-degree plunging anticline northeast. And then all of a sudden, every other geologist in the world can imagine what it is I'm talking about because they can see it in their heads, right? Okay. Here we have a thing. Isn't it a pretty thing?
Yeah.
It's a nice looking thing, isn't
It
it?
is a cool thing.
Yes, it's a pretty cool thing. What is it?
It's thing.
It's a thing, but let's be more specific. What's the next step up from thing?
Hill.
Okay, so there's a hill in there. But the structure,
Does it have to do with what we just learned?
it does have to do with what we were just talking about. Excellent deduction skills.
It looks like there used to be water flowing
Oh, you mean like this right here? Yeah, that's probably a river. But that's not actually having to do with the structure. What do you notice about these layers of rock?
Here, rock.
You're right. You're on a roll. All right, so we've got this layer of whitish rock and then reddish and then yellowish, right? But what do you notice is that they continue around like this, right? It's that white layer is the same layer going all the way around this structure. What you're looking at are vertical layers or near vertical layers of rock. You're looking at them in cross section. There's a layer, and there's a layer, there's a layer, and there's a layer, and there's a layer. And the same layers reflected on this side of the structure. And you can see where they meet each other around this end. So what could we be looking at here?
In anticline, but like it was weathered away.
All right, now we're talking.
You chop off the top.
If you chop off the top of this, right, you get a cross section exposed at the top of all the layers in this structure in cross section, right? Looking like that. Great. Why are they joined down here and not up there?
Because they're silly.
Huh? What happens if this that has been sliced off so that its layers are in cross section on the surface is also doing that? Where this tilted structure plunges into the ground at surface level, you will see all those layers meet up right there. Y'all ever had a Swiss cake? Where it's like layers of frosting and sponge cake that are all rolled up on top of each other. And you slice it. What happens if I slice it at an angle? Yeah, that's what we're looking at here, okay? The layers exposed in the cross section here are meeting up right here because this is plunging into the ground in that direction. It's doing this. Okay, into the ground. But here's the kicker. Marquez, in all confidence, said it's an anticline. How do you know that? Couldn't it be this?
It's one of them.
It sure is one of them, but how do you know which one it is?
Which way is north?
Which way is north doesn't matter.
The way I don't know. I tried.
I just don't know.
I tried.
Any ideas?
Head is empty.
No ideas. Got it. Okay. Well, should I just give you the answer then?
No, you should guide us through it.
Guide us through it.
Yeah.
Ugh, that sounds too much like good education.
Darn it.
Just give you the answer. Yeah. I think we both know that wasn't the option there. Okay. I guess purple?
Purple.
I've got red and green. Let's go purple. All right. I have 3 layers of rock. Boom. I'm going to hold these in the weirdest way.
That's kind of normal.
Boom, boom. Which one is older?
I would
On
assume
the one on the
gray
bottom.
hair.
Wait, why the one on the bottom?
The succession.
Ah, okay. What do we call that? Huh? Superposition. Great. Okay. So the one on the bottom, in this case, the green one is the older one. And the one on the top, the red one, is the younger one. Let's fold this sucker. Okay. We fold it and make an anticline. What's on the bottom?
The old.
The older one. What's on the top?
young.
The younger one. Let's make a syncline. What's on the bottom?
The old.
The older one. What's on the top?
The younger.
The younger one. Now, let's slice these off. Millions of years of weathering have reduced these down to surface level or near surface level. So now our surface is right there. We're looking at this from the top down. What do we see? For an anticline, looking at it from the top down, we're going to see that. What's in the middle?
Old.
Older. And what's on the outside?
Young.
Young. For a syncline, we're going to look at it from the top down. And what are we going to see?
Outside is the old and
The outside is the old, and the inside is the new. So how do I tell if something like this is an anticline or a syncline? With an anticline, the oldest is going to be in the middle. With a syncline, the youngest rock is going to be in the middle. Visually, they look almost exactly the same. I have to go closer and take a look at the rocks themselves to figure out what I'm looking at here. But he was right. That's an anticline. Not that he knew it.
Always
But always right, he says. Okay, so this is how we would figure that out. Does that make sense to everyone? Good. Yeah? Are you following along okay with this logic? Good. I don't want to leave anyone behind here. All right. Domes and basins work in a very similar way. I'm actually going to leave all that up there for a minute so that you can see what I'm talking about. A dome is when something from underneath pushes upwards, causing the layers of rock beneath them to bow upwards. Now, this isn't in a long linear fold. This is in a local area, say a magma chamber, a lava dome, pushes its way up slowly as it's crystallizing. Okay, but it causes the layers of rock above it to push upward into a dome shape. So in the middle, you would still get your older stuff because it's been pushed up. And on the outside, you would still get your younger stuff if I were to slice it off. With a basin, it's a low-lying area like that. But it starts slowly to fill in with sediment. So we've got sediment filling in our basin like that. See, and then we did purple. And finally, red is the youngest one. Like that. So if my basin later on gets weathered down, I'm going to get younger in the middle and older on the outside, just like with a syncline. Again, in a local area, not a long linear folded structure. Does the term basin mean anything to y'all?
Permian.
Ah, where is the Permian Basin? Here, we're in it. Why do we live in a place called the Permian Basin?
I would assume because we live either in or near a basin.
We live in the basin. This is the basin. But if we're calling this a basin, then that means at one point it must have been filled with water. This was at one point a low-lying area. In fact, it was a shallow sea that slowly, over time, over a time period called the Permian, which we will discuss more in 1404, it was before the dinosaurs, it got filled in with sediment. Layer after layer after layer. And all the sediment that we have here, well, the top few dozen feet that we've got here is far more recent. But the rock that we have underneath our topsoil here is Permian and older age rock, for the most part. That's why this is called the Permian Basin. All right, now we talked about folds. So we talked about faults last time. I told you about 3 different types of faults. What were they called? There's a strike slip fault. Good. That's the one where it's got that side-to-side motion. Normal faults and a reverse fault. In a reverse fault, the hanging wall is moving up relative to the foot wall, which, by the way, usually means you get some sort of highland or mountainous area on your hanging wall. In a normal fault, the hanging wall is moving down relative to your foot wall, which means that you've got some sort of highland or mountainous area on your foot wall. In a strike slip fault, you don't really get any of those highland areas, like the San Andreas. Now I'm going to tell you about a third type of fault, a thrust fault. This is responsible for a lot of the larger scale mountain range complexes that you may be familiar with, such as the Rockies. Okay. In a thrust fault, it's very similar. It has the same compressional force as with a reverse fault, by the way, but the mechanics with a thrust fault are a little different. Notice, if you will, that my reverse fault slices through the layers of rock. So these two that I've outlined here, these red layers here, are the same layer, but they have been sliced apart. The two halves have been sliced apart, and one is up relative to the other. In a thrust fault, the same compression stress occurs, but the fault happens along the boundary between layers of rock, not slicing through them. So we've got our thrust fault right here at a much lower angle than my reverse fault. My reverse fault might be here. It might be a 45, 50, 60 degree angle. A thrust fault, usually much lower, 10, 15 degrees max a lot of the time, okay? Because it's going between layers of rock. So I might have a shale layer getting shoved on top of a sandstone layer. But these can go for much longer distances. They go a lot further than the reverse faults. Why? Why might physics like thrust faults for moving material a longer distance?
Because it doesn't have to go as much of a steep angle.
Yeah, it's the angle. How easy is it for you to push a car up a hill versus on a flat surface? Has anyone here ever had a car that died and you had to push it? Of course, you and me, right? That makes sense. You've had to? Okay, a lot of the newer cars, that's less of a problem, I think. There were a lot of the older cars that happened quite often, okay? If your battery dies, it wasn't always just convenient to jump it, right? And there weren't all those helpful towing companies every other block. But when you're pushing your car over a flat surface or a near flat surface, it's significantly easier. That physics is the same for rock. So if compressional forces have to push rock over a low angle, they're going to go a lot further because they're fighting gravity a lot less. Whereas with a reverse fault, it's still going to shove up, but it's not going to go nearly the same horizontal distance that a thrust fault will. So there are various mountain building events that have happened as a result of thrust faulting. Like I mentioned, in our West Coast, the vast mountain ranges that we have in the middle of the United States, the Rocky Mountains in particular, are largely due to thrust faulting after thrust faulting events that occurred. Okay. But what do we call those mountain building events? We call those orogenies. And orogeny is a mountain building event. Orogenesis is the process of mountain building. They obviously come from the same root there. Just make sure you're using them in the right context. Orogenesis is the process. Orogeny is the event. So I would say, in a sentence, just as an example, the Laramide orogeny was responsible for a lot of the current Rocky Mountain building, okay, geographic complex, okay? But I would say this orogenesis caused, right, in that context, I'm talking about the process, okay? So just keep those words, keep those two different straight, because they can get confused pretty easy. So let's talk about different mountain building events, different orogenesis, okay? So you can get mountain building through volcanic island arcs. This happens when two ocean plates run into each other, converge with each other. We talked before that when an ocean plate and a continental plate run into each other, what happens? Continental plate, ocean plate. It subducts. The ocean plate subducts. Why?
Because it's denser.
It's denser material. Continental plate, less dense material. The denser one will always subduct. What happens when two ocean plates run into each other? Huh? They're both going to go down? Well, they can't both go down. Can't do that. They go up. Can't really go up. There's not much mass to them. There is some mountain building as a result of what happens here, but not because they go up and make a big mountain range. One will subduct still, but in the case of two ocean plates, which one is going to subduct? Whichever's denser. Yes. But how do you know which one's denser? Which one is going to be denser? The deeper one? What do you mean?
Like if it's close to the land and the one deeper in the water.
Oh, I see. Relative to relationship to their land. No. No, actually. That's not part of it. But good idea. Good thought. What would make one ocean plate denser than another? Obviously, one didn't go to high school. Right? No. What for real though? What would make one denser than another? Huh? The amount of mafic material with it. Let's pursue that. What would make one plate have more material than another? Let's assume the composition is the same. What you're talking about is one having more. We're talking about quantity, not quality here. What would dictate one ocean plate having more material than another? There are no dumb answers here. Spit them out, huh?
If the oceanic crust is closer to the mantle,
If the ocean crust is, they're at the same depth, okay? They're about the same. It's just we're talking about one being thicker than the other, right? In Abby's example here, why would one be thicker than the other? What? Organisms don't have anything to do with it. But again, I'm loving the ideas you're throwing out. Keep them coming. We'll get there eventually, huh? Not salt.
What about a magma chamber in the crust?
No, that would be a local occurrence, not something that would be true. You're thinking way too hard about it. All right, let me give you
there's one
Ha! There it is! I didn't have to think of an example. One of them is older. In the case of two oceanic plates running into each other, one of them will subduct. Which one's going to subduct? The one that is denser. How do you know it's denser? Because it has more material and it is cooler. Cooler, therefore meaning more dense as well, right? So the warmer, younger oceanic plate will override the older, denser, cooler oceanic plate, which will subduct. Does that make sense? Same physics. You just got to think about it a little more. Okay? So we have an older, denser ocean plate subducting under a newer, younger, warmer, overriding ocean plate. Now, what happens here? The same thing that happens in the original situation, right? Where you've got your subducting plate going down into the mantle, introducing water to the mantle. What does water do to the mantle? It reduces.
Volatile.
Yes, it's adding volatiles, but it's reducing
Pressure?
Melting point.
melting point. There it is. Water reduces the melting point. Dropping the pressure was another way to do this, but that's at a divergent boundary, right? In this circumstance, you introduce water to the mantle. You reduce the melting point of the mantle rock, meaning that you get more magma. The magma rises up to the surface and makes a chain of islands. We call these a volcanic island arc. This is Japan. Okay? Japan and a whole bunch of other islands out there in the Pacific. Those are volcanic island arcs. Okay? Then we've got our Andean type, where we have an ocean plate subducting under a continental plate, doing the exact same process, but there's something different here. In our first example, this magma is rising up through a top plate of ocean crust. There's not much time for Bowen's reaction series to happen. Okay? Which means that we get islands made mostly out of mafic material, at least initially. Gradually, as this rock gets thicker and you start to make bigger and bigger islands, Bowen's reaction series will have more time and you'll start to get more intermediate material in there. But for the most part, it's going to be basaltic. It's going to be mafic. Here, though, where we already have a thick crust of continental material, Bowen's reaction series has plenty of time to happen, which means that by the time your magma reaches the surface, it's intermediate to felsic. And it just adds to the felsic nature of the continent. Okay? Same principles, different lengths of time for Bowen's reaction series to happen. Then we've got accretionary belts. What happens when my volcanic island arc that I made in that first example is on the plate that it is on, right? That volcanic island arc got built up on the overriding plate. What happens when that overriding plate becomes the subducting plate? It switches, right, to being the one that's sucked underneath another plate. Okay? My volcanic island arc all of a sudden runs into the subducting plate boundary. It gets scraped up off the side of the oceanic plate. It's just scraped up off the edge and shoved onto the side of my continental plate. And so you get island after island that just gets scraped up onto the side of this continent while the ocean plate keeps getting subducting underneath. And that's how you make California. The west coast of the United States, in particular the California coastline, is basically dozens of volcanic island arcs that have gotten scraped up onto the side of North America. A huge chunk, I might even go so far as to say half of the geologists in the United States that study these processes live in or work in or study California geology. Because trying to untangle the mess that is California, I'm talking about the geologic mess in this context. It's a mess for many other reasons. But the geologic mess is a work in progress. I'm talking dozens of islands that have all just gotten scraped up on top of each other, each of which brings their own different flavor of fossils or geologic histories. Okay? And then we have collision belts. When two continents run into each other. Can you think of an example where this is happening? Yes, India running into the megacontinent of Eurasia, right? The Indian subcontinent running into that continent has made the Himalayan mountain range. That is an example of continent-continent collision belts. Now, one does slightly subduct under the other, but for the most part, things go up, making our mountain range, and things go down. That mountain range usually has roots that go very, very deep underground. Now, this isn't so much a mountain building method per se, more of a mountain continuation method. It's called isostatic adjustment. Y'all ever put your head on a memory foam pillow? And then you put your head back up and it slowly rebounded upward? I used this example when we talked about glaciers, right? When we talked about isostatic adjustment for glaciers. Well, when you have a mountain range on a continent, that's a lot of rock. And it pushes its way, forces its way down that massive rock a little bit into the mantle, underneath your crust. That much mass can't be contained all on the surface. It sinks down a little bit into the mantle. But as weathering and erosion slowly remove material from the top of my mountain range and carry it away, I am removing mass, right? It can no longer push as much into the mantle. So the mantle rebounds upward a little bit, like that memory foam pillow, pushes the mountain range upward. Which is why we don't just reach a point where on the surface of the crust, we have a flat area that used to be a mountain range. That doesn't really happen. Instead, the mantle continues to push upwards on the roots of that mountain, shoving them upwards. And so where we once had the top of the mountain range here, now we have exposed mid-mountain range on the surface because everything else got eroded and removed from on top. And then at the very end of a mountain chain's life cycle, you've got the deep, super metamorphosed crystalline rock exposed at the surface. The stuff that once was shoved down deep into the mantle is now exposed at the surface because of this isostatic adjustment. And so, yeah, it keeps mountain ranges relatively high for a longer time than you would think because the roots are getting shoved up out of the mantle as they weather from the top down. Okay? Any questions about mountain building? Right then. You ready? Let's review. Don't need the PowerPoint probably for this. If we do, I'll just turn it back on. Review time. Hit me. Yeah, no. Figuratively. Check this recording and make sure that it's not bugging out on me.
How many questions does it have?
Great question. I will give you the statistics as soon as this picture loads and lets me know that it didn't crash. I'm afraid it may have crashed. Please don't have crashed. It probably crashed. Page unresponsive. I don't like this. Really don't like this. I'm so cooked. All right. Well, we might as well. Oh, hello. I really hope that it's been recording this whole time. No network connection, trying to reconnect. Find a stronger signal. Brother, it's plugged in. All right, I'm going to end this and start a new recording for the exam review.